Welcome to my GIS lab. We will discuss some basic terrain analysis, slope and aspect, and how to display them to tell your story. And then we discuss two raster geoprocessing tools that you may use very often: the Reclassify tool and the Zonal Statistics tool. I have a 10-meter elevation model and I want to carry out some basic raster analysis. The raster tools are under our spatial analyst tools, and within there, under our surface analysis, I'd like today to carry out the slope command and the aspect command and just cover some basics. I have here the result of my slope raster, and we see I had my hill shade already turned on, how without the hill shade the resulting slope raster does look very chaotic. And the moment we turn on the hill shade, things are organized, we understand where the ridges and where the valleys are. The default color scheme chosen by ArcGIS is not the color scheme what we want. Slope has its own color ramp. We can change that, of course, by going to our symbology. And the easiest way to find a particular type of color scheme is by turning on your names, and the names are simply sorted alphabetically. So if I go down here, find my slope. So then I can apply the slope, and there would be the appropriate color scheme. Right now the default is that we have lots of classes in here. In this case it's overkill. We don't need all these ones. The story can be often told in a much simpler way. Here is a slope by only using 6 classes, and the class intervals here have been chosen. We can very clearly distinguish between the steeper slopes along the ridges and the very shallow slopes of under 3% over here. So this is already an important part. I just mentioned percent. Slope can be, of course, in degrees or in percent. Two things here. We see that our largest value is 166%. So this slope raster cannot be in degrees because now we have a value that is larger than 90 degrees, and so this therefore cannot be a slope raster in degrees. I also personally like to always, in my raster output file, slope per for slope percent. And also whenever you see a resulting layer file, we can go back to the catalog, and within the catalog, if you go to history, we can go and look at the parameters that were chosen to create the slope in the first place. So in this case here, my input file was my 10-meter elevation model, where it was put, and here output measurement percent rise, otherwise it could have been degrees, and then the other variables. And even better than that, if you double click on your history, then it opens up the tool already pre-filled out how it was, so we know exactly what happened. And if you wanted to make a change, well, you make a new output file name, change some parameters, and rerun it. So there is a history of your commands that you simply have to find. So there is your log, you know exactly what you've done and how things were created. Maybe we don't need 6 different classes. Maybe our story can be told with only 3 classes. And here now we have a very similar story, red, yellow, and green. And we divided our landscapes into anything that is steeper than 15 degrees and less than 3 degrees. Very often in GIS analysis, we only need certain threshold values. For instance, there is a threshold value for road construction or for pipeline construction or for forestry or for agricultural land. And once you know those thresholds, then you can apply them in your symbology and therefore make a map that is meaningful to the user. And we can make the map even more meaningful by editing our labels. And now the results are easier to understand by the public, or they follow specific conditions relevant to a particular application. And here are some observations about the edges of our raster when we calculate them. Let's zoom into the corner quite a bit. And here we now see that the hill shade that we calculated from the elevation model is exactly 1 grid cell less on the edge. The reason for that is that the hill shade calculation requires a window of 3 by 3 cells, and if it doesn't have a cell on either side, then it calculates no data for that hill shade cell, and therefore then results in lesser cells. The exact same thing happens also for our slope, where the slope raster is exactly 1 grid cell smaller than the elevation model. Please remember that. Rather take an extra large extent for your raster file so as to avoid any edge problems that you may face otherwise. Finally, what we can do, instead of simply symbolizing our slopes into, in this case, 3 different classes, we can create a new output raster file that contains only these specific 3 classes. And we can do that with the Reclassify command. Which we find under the toolbox Reclass, and here's our Reclassify command. My input raster is this one here. My reclass field is the value, my slope value. And I want to not use unique values, so that means all the values that are listed in here, way too many in our case. I want to classify all my values into 3 classes. Here are my 3 classes, numbers simply 1, 2, and 3, and the last thing I have to do is give my value range, so it starts at 0 slope, and in our case I want 3, and then the next one goes from 3 to 15, and the other one goes from 15 to the maximum. We give it an output file name. I call it foothills slope, and then rec for reclass, and I like to add additional information in my file name, so in my case it reminds me that I have 3 classes. And I hit run. And here is a new raster file. When we open the attribute table, we see the value and count, always the only important fields. Count, simply the number of cells with a particular value. We only have 3 different kinds of values. And finally, we want to improve the symbols. And I move my hill shade on top. And now we have a map that we can use for further analysis. And not only a map, but also a database that is directly now with burned-in values that can be used for instance, an environmental model. Moving on to aspect. Here is the correct color ramp for aspect. And it already automatically divides our raster into 8 different directional classes, and these are then going through the color ramp so that we can distinguish between east and west and south and north facing slopes. Two things I want to mention about the aspect. The one is we have here a class value of -1 for flat. So flat means slopes of 0. You cannot calculate the slope direction when the slope is 0. Aspect is meaningful where it's relatively steep in very flat areas like the river valley that we had over here. There we have aspect values that look the same as those on the ridges. So aspect doesn't care if your slope is 1% or 100% and gives it the same aspect value. And that can be very confusing when you apply aspects and apply them especially for decision-making processes. I have here also my land cover file that we used before. And here we can now get the idea that we may want to find out, is there a relationship between our land cover and our elevation or our slope or our aspect? And we can investigate that by using the Zonal Statistics command. Again, going back to my history, let me open up one of my statistics tools that I used here. So I used Zonal Statistics as table, so the output is a table. And in this case here, what I'm doing is I want to find out within my individual land covers that are in my land cover file as grid code. Within each of these different classes, what is my average aspect? Or if I use my slope file, what is my average slope? Or if I use my elevation file, what is my average elevation within each of my individual land covers? And then when I was hitting run, I am creating simply tables. Let's open up these tables. So here's my table. It's not an attribute table, it's a standalone table. I have here my 8 different land cover classes that are in my land cover file. And right now the only one of importance for me is my mean elevation. I make sure I'm sorting from, in this case, lowest elevation to highest elevation. And these are the mean elevations within each land cover type. Let's take cropland in yellow for argument's sake. So here is my lowest elevation. I have my minimum and my maximum values over here, and I have a whole bunch of other statistics that I don't need. And we can clearly see that there is a logical progression that we have, and let's turn on our legend so we can now see the grid codes and what they mean. So the next highest is deciduous forest in the valleys. And contrasting this, in the highest areas, other than snow, water, and bare rock, we would find coniferous forest number 5, which we find has the highest mean elevation. And then that is followed by, we're ignoring right now, bare rock and snow, and mixed forest is the next one, and then followed by grassland, and back to deciduous forest. So there is an interesting logic in the distribution of our land cover as a function of elevation. Let's investigate slope. I again make sure that they are sorted from highest to lowest. So right now number 6 is bare rock. Well, that needs to be investigated why that is. Here is so a certain logic that we can find number 1 and number 2 again, cropland and deciduous forest, down in the valleys with the lowest slopes, very shallow there. And then again contrasted by number 5, which has clearly the steepest slopes. So again, there is an interesting story there. And if we open up our aspect, With our aspect, there is not much variation. The lowest value is basically southeast, and the highest value has an orientation of just a little bit west of south. South would be 180. So there is no clear relationship between aspect and land cover for this part of our study. That's all for today. Until next time.